Okay. Welcome to Knowledge Share channel. It's my great pleasure in welcoming you all again. To introduce myself, I am Dr. C. Uday Shankar, Senior Innovator in SNS Institutions. Today here I am to present about Kirchhoff's voltage law. As you all know, Kirchhoff's law plays a very vital role in determining the voltage and currents in the given circuit. In this sequence of videos where I will be discussing about different things which are to be known in electrical basics. So in this I will be discussing about Kirchhoff's voltage law. So what do you mean by Kirchhoff's voltage law? So in any network, the algebraic sum of voltage drop across the circuit elements of any closed path will be equal to algebraic sum of the EMFs in that path. That is, we can also say like this, like the algebraic sum of all the branch voltages around any closed path or closed loop is always 0. And in this law, for example, if I am starting at one point of the closed path and then I have to go on tracing all the potential changes in that particular direction till the starting point is reached again. So this is how you will be performing the Kirchhoff's voltage law. So when you do so, for example, you will be observing sum of potential rises must be equal to sum of potential drops in the given circuit. So the total change in potential along the closed path will always be equal to 0. And this is a very important law which will be useful for circuit analysis of any given network. So we will be having two different things. One is potential rise, the other one is potential drop. See, for example, if in case of potential rise, it may, for example, if I am traveling from negative to positive, then the terminal is terminal should be marked as positive. If I am traveling from positive to negative, then that particular terminal should be marked as negative. So you can go in any direction. You can go with either clockwise direction or you can go with also negative, that is anti-clockwise direction. It is independent of your choice. See, for example, see here I am having a network. Okay, so here I am having a network, a closed loop complex network is there. So with various branch currents have been marked on the particular circuit, and I can see that the branch currents are assumed to be different from each other. Okay, so it's not the same branch current, it is something different. Okay, so here you can see that the polarity of the voltage drop along the current direction is to be marked. Okay, so from here you can see that the equation will be something like this. See here, I will be putting the equation. See, just a minute. So here you can see that in this diagram. So I will be going from this end. Okay, so I will be going from this end. So I will be going. See, for example, I will be going in this direction. Okay, so this is what I have done over here. This is what the detail over here. Okay, so here, for example, if I am starting from this A, B, C, D is there. So here A is there. Okay, B is there. So I am just going in the same direction, A, B, C, D. So R1 is there. So you can see that R1 is potential drop. So you have to put minus. So minus I1 R1 is there. So since I am moving from negative to positive, this has to be plus E1. And similarly, this is I2 into R2. So why? So again here I am putting minus because it is a potential drop. So again you can see that minus I3 R3 because it is a potential drop. So whenever there is a potential drop, you have to write as minus. You always, all the potential drops will be equal to will be having the negative sign. Where, and similarly you can go with here. So here you can see that minus I4 R4 and similarly plus E2. Why it is plus E2? Because I am moving from positive, negative to positive. So here again it should be positive. So from this equation, if I just rearrange, you will be getting an equation something like this. So for example, if E1 is given and E2 is unknown, you can sorry, you can easily find what is E2. So this is how this KVL is working in determining the unknown voltage values. Okay, so it's very important to understand that is the potential drops should be always with minus, whereas the potential rise can be positive or negative depending on whether it is from negative to positive or it is from positive to negative. So if it is from negative to positive, then we have to put it as positive. Then if it is from positive to negative, then we have to put it as negative. So all the voltage EMFs, okay, will be having positive or negative according to the direction of voltage source, whereas all the potential drops, that is with resistance, will be having the negative value. So from this we can see that around a closed path, that is, this is a very important thing. Finally we conclude that around a closed path, the sum of voltages should be equal to 0. And so this is a very, so while applying KVL, the direction in which the loop is to be traced is not important, but the sign convention is most important. So please understand it. And so this will be applicable for all the closed loop only. Okay, this will be applicable only for all the closed loop only. So thank you very much for your patient listening, and that's all for now. And any queries, please let me know in the comment section. And if you are really interested to know such videos, please subscribe to this channel. And if you really like this video, please give a like to this video. Thank you.